want to start with a small correction. I did try to draw the picture for this example, but I forgot that the critical points were 0, 0, 1, 1, and minus 1, 1. So I forgot that the height here should have been 1. That's the correct picture. I just put the set of points a little bit up. But still, the general shape should be somewhat like this. Okay, so we talked about local maxima and local minima, but to be honest, they are not what is important. What's important is usually the global maxima and global minima. We want to find the actual best values, not just the values which are locally the best, which you cannot improve on by small changing parameters. You want to find the value of the parameters in your problem for which the quantity you're trying to optimize is the absolutely largest. So we talk about absolute maxima and minima. So we say point xy is the absolute maximum point for f on the domain D. So in typical application, we want to talk about a function of two parameters. Let's say the production level is a function of labor cost and capital investment. And we want to optimize this function subject to some pretty mild constraints. Something like the production cost is positive, the capital investment is no larger than 1 million. So in the two-dimensional space of all possible pairs of parameters, we have a subdomain. Only the values of parameters which are interesting for you for some kind of physical reasons, because the problem comes with some constraints about the parameters. And then the question is, among these parameters, at what point xy the value of the function is the largest? So a typical example would be find the absolute maximum and minimum of squared minus 2x plus 5 on x squared plus y squared makes more equal to 0. So in this example, you are given a function of two parameters. For each pair x and y, you can compute what is the value of f of x and y. But you are only interested in those parameters, those pairs x and y, for which x squared plus y squared is more equal than 4. So basically talking about the restriction of your function to a disk of radius 2. For each point inside of this disk, you are interested in the value of the function, and among all the points, you want to find the point where the value is the largest, and the value where the point where the value of the function is small. So, how to approach this question? first of all, you want to find the critical points. You want to find out where are the local maxima and local minima. So to solve, to find maxima or minimum of function on domain, you want to do the following steps. First of all, find the critical points inside the domain. Unfortunately, this is not enough. Even in one dimension, it was not enough. If you wanted to maximize a function on some interval, it wasn't enough to find the critical points inside the interval. Maybe a function keeps increasing all the time, all over the interval, and there are no local maxima, no local minima. Still, there would be some maximum and some minimum for the function. There will be a largest value and the smallest value. In one dimension, all you have to do is check the endpoints. Here, well, what are the endpoints? Here they are called the boundary of the domain. So these are the points where you can only move in some directions to stay in the domain, but not in all possible directions. So what distinguishes the interior of the domain from the boundary? In the interior, if you go in whatever direction for a small distance, you stay inside of the domain. For a boundary point, something here, if you go in some direction, you might go inside the domain. In some other direction, you'll go outside the domain. So such points are called the boundary of this domain. So the next step is find the maximum or minimum of f on the boundary. And third step is compare the values of f and critical points and the maximum or minimum on the boundary. So admittedly, this algorithm, well, kind of algorithm, by steps, admittedly, it's not so restricted. You can't really follow it. And the reason is, step 2 is quite complicated. You are being asked to find the largest value of your function among infinitely many possible values. We want to talk about all possible values on this circle. We'll learn a little bit later how to do this step quite systematically, but for now let's consider just one example. This particular example, I'll continue the same question. Oh, by the way, another remark. Why is it that the boundary should be actually treated separately from the inside of the domain? Well, when we talked about a point of local maximum and local minimum, and the fact that the partial derivatives at such point are equal to 0, well, we kind of assumed that we can actually move in that direction, we can actually move in that direction, and that the rate of change in this direction tells you something about the, well, how fast the function is changing around this point. At a point on the boundary, it's not true that you can move, well, in this direction or you can move in that direction. Because actually we will fall outside of the domain. So the partials tell you only, well, part of the story for points on the boundary. For points inside the domain, well, still the same considerations applies for just function on the whole plane. So let's talk about this question. Find the absolute maximum minimum of that function x squared plus y squared minus 2x plus 5 on this circle. So solution for exercise. First of all, I want to find the critical points inside the domain, not on the boundary. So find the critical points in x squared plus y squared smaller than 4. I want to look at the inside of this circle. That's the inside. I want to find the critical points. Let's do this. A critical point by definition is just a point where the partials are equal to 0. The partials in this case are 2x minus 2, and the partial relative to y is 2y. I want both to be equal to 0. So it tells me that x equal to 1 and y equal to 0. So in this case, it's quite easy to find the partials. So critical points. There is only one. Here it is. Step 2. I'll try to find the maximum and minimum of this function on the boundary of the domain. So as I said, for now we don't have general tools for doing this. So we'll do it small tweak in this particular example. This function is complicated. X squared plus y squared minus 2x plus 5. But if you restrict this function to the boundary of this domain, what is the boundary? So on the boundary, well, it's just this circle, not the whole disk, just the circle. X squared plus y squared is equal to 4. On the boundary, you can replace this complicated function, which is x squared plus y squared minus 2x plus 5, by a much simpler one. I know that for any point on the boundary, x squared plus y squared is actually 4. So this complicated expression is actually just 4. So it's a trick. It happens that this function becomes much simpler when you restrict it to just this circle. It's not true that it's the same as this function all over the disk, but on the boundary, on the circle, it is. And now for this function, it's not that hard to find what is the largest value and what is the smallest value. Just think about it. You have this circle. How can you make 9 minus 2x the smallest? Well, try to make x as large as possible, which means try to go to the right as far as you can. So it's over there. You can go only up to the point where x is equal to 2. So maximum, minimum at 2.0 and maximum negative 2.0. So once again, we're not following here a general procedure, it's just a trick. The largest possible value of this, let's start with smallest one. Smallest possible value of this function on this circle, well, how can you make this expression as small as possible? Just try to make x as large as possible. And how large can you make it? Well, the largest value of x on the circle is 2. And it's achieved at the point 2.0. So the largest x is right here. What about the maximum? Well, for maximum, you want to make x as small as possible. So you want to move to the left. How small can you make it? Well, move to the left. Right here is the smallest. So it's not really something that, like, in each example you will be able to find such a nice trick, but well, I chose this example because there is a simple trick which can solve this type. Okay, and finally, once you know the logical function on the boundary, the smallest value of the function on the boundary, and all the critical points inside the domain, you can just compare. It doesn't really matter whether this point is local maximum, local minimum, you just compare the values of the function. So, step 3. Compare f1,0, f2,0, just compute. F of 1,0 is 1 plus 0 minus 2 plus 5, or 2,0 is, okay, you can use either this expression, maybe this expression, because it's on the boundary, so it's 5. F minus 2,0 is 13. So just comparing these values, I see that this is the minimum and this is the maximum. So this function, well, it behaves in a funny way. It becomes the smallest possible somewhere inside the circle. Then it looks like it is increasing from this point in all directions, but then it doesn't, then it increases. At some point it has the value 5, at some other point on the boundary it has the value 13, and all other values on the boundary are between these numbers, between 5 and 13. So, once again, for now, we just know how to do the first step in all kinds of examples, how to find the critical points inside the domain. We don't know, once again, for now, how to perform the second step. We'll learn a little bit later. And step 3 is very easy.
How do we get f of 1, 0 equals 4?
You just plug in 1 squared plus 0 squared minus 2 times 1 plus 5. Yeah.
I'm sorry, but for step 2, sorry, asking this, how did you get the minus 2, 0 circle and the max and negative 2, 0?
Okay. So I argue this. On this circle, my function is just 9 minus 2 times x. How can you make 9 minus 2x as small as possible? What should you do to x? Make it as large as possible, because they're subtracting 2 times x. Well, how can you make x as large as possible, but still staying on this circle? Right here. And similarly about the minimum. So it's just a lucky coincidence. Both the shape was very simple, the function restricted to the boundary was simple, but later we'll learn how to deal with more complicated functions.
What's confusing me is like 9 minus 2x is the function, right? So if you plug 2 in, how come I don't just do 9 minus 4, which gives me 5?
Yeah. Well, 9 minus 2 is 5. Right. 9 minus 2 times 2 is 5.
Yeah, but you plug that into the original equation as well, so what's the correlation between those two?
They're exactly the same thing on this circle. That's the point. On the circle, when x squared plus y squared is equal to 4, this expression and that expression give you the same answer.
I see.
It's not true inside the circle, it's not true on the disk. So if you try these two expressions at this point, they'll give you quite different answers. But on the circle, they're the same. Yeah.
I don't know if so that x squared plus y squared equals 4 that can be substituted into the full equation.
Mm-hmm.
Okay.
Yes. Okay, so at least now we, oh yes, and the comment about this kind of algorithm, this outline of what we have to do, it works often but not always. So let me give you the precise conditions when this algorithm does work. So the problem is sometimes the function just doesn't have a maximum or doesn't have a minimum. How can it happen? Well, even for a function of one variable, it could happen that it had no maximum or no minimum. For example, if it was a function not on a bounded interval, but on the interval from 0 to infinity, and the function kept increasing all the way to infinity, then it has no maximum. So the problem could have been that the kind of domain is not bounded. You can go all the way to infinity. Another trouble, even in one dimension, was if the endpoint, kind of the function wanted to achieve some maximum at an endpoint, but the endpoint happened to be outside of the domain. So somehow the domain did not include its own boundary. But for a function in a closed bounded interval, well, we had the following fact: a function which is continuous has a maximum and a minimum on a closed bounded interval. Same thing happens here. So, all right, just as a fact, a continuous function continuous has the same meaning for a function of two variables as it had for a function of one variable. A small change in the argument leads only to small change in the value of the function. So the function doesn't jump suddenly. And most functions that you are likely to encounter will be continuous. So a continuous function has a maximum and a minimum on a bounded closed domain. So I use two words which need explaining. I'll explain them in a second. First of all, bounded. One can't go arbitrarily far inside the domain. So you don't want somebody to be able to escape kind of infinitely far from the origin, staying inside the domain. So on a disk, well, you can only go distance of 2 from the origin. But if it was something like, I don't know, the entire half plane, just move all the way in the direction of this half plane, you'll escape to infinity. Well, you want to eliminate such situation. And closed means all boundary points are inside. So like here, the boundary was a circle and it was inside the domain. If I change it, instead, if I change the domain to be x squared plus y squared is strictly smaller than 4, you would have a problem. The function would want to assume the value of 13 at the point minus 2, 0, but this point would be excluded from the domain. So if these two conditions are satisfied, if the domain is both bounded and closed, then a function has a maximum and a minimum, and that's the way to find it. So let me just give you some typical examples of domains which are bounded closed or not closed and bounded, or different combinations. So bounded closed like this, some kind of domain which is kind of a finite blob in its plane. Something which is not bounded. Let's say closed would be something like this. So in this domain you can go infinitely far from the origin and staying inside the domain, so it's not bounded. And you can imagine that a function on this domain can just keep increasing in this direction and have, say, no maximum. Something which is bounded but not closed. We'll just take a similar picture, but just exclude a couple of points on the boundary, or all the points on the boundary. So just throw away part of the boundary, and now you can imagine that a function might want to attain some maximum at a point of the boundary, but if you throw this point away from the domain, well, there is no maximum. And of course something which is not bounded and not closed. Just take such an example, maybe inside of a parabola, something where you can go infinitely far, and also throw out something from the boundary. So such domains are good for us. Any function would have a maximum and minimum. Such kind of domains are not that good. And we will not discuss optimization problems on such kind of domains. So eventually we'll want to know how to find the maximum and the minimum of a function on a boundary of some domain, on some curve. So restrict the function not to the whole plane, but just to some curve, and find the maximum and minimum. Before we can do it, we should discuss the notion of gradient. So even before this, I want to talk a little bit about approximation of a function of two variables. So let's talk about linear approximation. So I'll start with a reminder. If you have a function of one variable, you have a very nice way to approximate it if you know the derivative. That's the way. F of x plus a small change in x is approximately f of x plus the value of derivative at the point x times the change in x. So that's just a formula from the previous course. Change in the function is proportional to the change in argument, and the coefficient of proportionality is called the derivative. For a function of two variables, I want a similar formula. I want a formula that will tell me if I change the argument of the function by a little bit, how much the function is going to change. Well, we already know two answers. One is like this. What happens if you change x a little bit and keep the y? Just don't change y. Well, the function is going to increase by the following amount. The change is going to be proportional to the change in x. The coefficient, well, it's the derivative of f relative to x. Because here you keep y fixed. So this derivative is the partial derivative of f with respect to x at the point xy. Similarly, you know that if you want to change y but keep x fixed, what's going to happen is your function is going to increase by the following amount. Delta y times the derivative of f, but now relative to y. You change the y, you keep x fixed. So we have these two approximation formulas. What I'm really interested in is what happens if I change both parameters, both x and y. So what do I get if I change x by delta x and y by delta y? Well, here's the answer. If I change the x, I'll add to the value of f this amount. If I change the y, I'll add this amount. If I first change the x and then change the y, I'll first add this amount and then add this amount. So overall the change will be this. Plus the partial with respect to y times delta y. So if I do both changes, I can think about them as doing first one change and then the other one, and that's the result. I perform the first change, then I perform the second change, that's the overall change. A short way to write down the same result is as follows. The change in the function is approximated by the following amount. The change in x multiplied by the partial with respect to x plus the change in y multiplied by partial relative to y. So please remember this formula and understand that what it means is exactly this pair. So let's look at a simple example. If the production level question is if k changes from 10 to 11 and L changes from 20 to 19, how much, how does it change? Well, the question is just approximately. So you want to estimate the change in the production level if you perform two simultaneous changes. You both increase the capital employed from 10 to 11, and you decrease the labor employed from 20 to 90. Well, of course, in this particular example, you could just take this simple function, evaluate it at 2 points, at the point 10, 20, and at the point 11, 19, compare the two values and see what the change is. Well, maybe it's not the most pleasant thing to find out what is the cube of 11. So what you want to do is just approximate, find an approximation. And for more complicated functions, it would be even harder to do it in the direct way, but still should be relatively simple to do it using approximation, using this formula. So the solution will involve this formula. The change in the production level is going to be approximately the partial derivative of the production level relative to k multiplied by change in k plus partial with respect to L multiplied by change in L. What do we have here? We have that the change in k is equal to k went from 10 to 11, so the change is just 1. The change in labor went from 20 to 19. The change is -1. The partials. Just take this expression and find the partial derivatives. So 3k squared plus L and 2L plus k. Well, we want to evaluate these derivatives at the original point, at the point from which we are making the change. So at point k is equal to 20, k is equal to 10, L is equal to 20. The partial derivative relative to k is 3 times 10 squared plus 20. 320. The partial relative to L is 2 times 20 plus 10 is 50. And now plug everything to this formula. Delta P is approximately 320 times change in k, which is 1, plus 50 times -1, so it's 270. So now you know, if you make these changes, both to k and to L simultaneously, the change in production level will be, well, approximately 270. When you're talking about this formula, well, you want to make sure that these delta x and delta y are small enough. So this example looks like they're small enough. Delta x is just 1, and it changes from 10. So 10% kind of reasonable. Okay, so any questions about this approximation? So next time we'll start talking about this expression of how to optimize a function, but on the boundary of the domain. Inside the domain, that is boundary. So, okay, see you.